Hello, everybody. Sorry about the delay. Had some hardware issues. This talk we're going to discuss two games that we wrote for examples in our spare time at ICS, and some of the lessons we learned, the approaches we took, and what we learned and how to do things in the future. The title of this presentation was originally simply the Dance Dance Cute Revolution, which we had planned to do a demonstration of the code, a walkthrough, how it was built, and then finally actually play the game on the dance pad where you could watch me make a fool out of myself, and then I would invite all of you to likewise have a dance on the pad and play a few games of Dance Dance Cute Revolution. Unfortunately, while the pads made it through customs, the box that had the adapters in it that would allow me to plug it into my computer via USB did not. In fact, they're still stuck in Cologne, Germany. So I have re-engineered the slides a little bit. We're going to talk about still Dance Dance Cute Revolution and what works and how QML was a good choice for developing that type of app. We'll also talk about an application called QML Bounce, which was also written by ICS as a demonstration on Nokia Developer. It's a side-scroller game with a completely different approach to writing games, so we can get some compare and contrast. I will be able to show you the Dance Dance game on my computer. I have modified it so I can play it via the keyboard. Unfortunately, it's just going to be a lot less fun than I had planned. So without any further ado, let's hop into the slides and see what we have. I am Justin Noel. I'm a senior consultant from ICS, Integrated Computer Solutions. We are North America's largest Qt consultancy firm. I spend about 75% of my time actually writing code for our customers, making devices, applications, mobile phone things, and about 25% of my time teaching courses, doing presentations like this, which roughly maps to what ICS does. We are primarily a consulting company and also a training resource. We have a lot of training videos on our website for free if you would like to, learn things like, how to do threading in Qt. Go to ics.com. We have a section called the ICS Network. So now that the advertising is done, let's go ahead and talk about the game, this Dance Dance QML Revolution. It is written entirely in QML and JavaScript. We were sitting around, lunch for a few days, deciding what applications could we write as sort of little test beds to see what we could do with QML, figure out what things are easy and what things are hard. And one of my coworkers, Tej Shah, he's a big Dance Dance Revolution fan, plays an open source version of it. It's like, that'd probably be a pretty good, language and environment to re-implement, Dance Dance Revolution. And so that's sort of the path it started. And we set as a goal for ourselves, we should try and do this entirely in QML and JavaScript without touching C++ at all, kind of as a challenge to ourselves. So some of you may not have seen this before. Started out life around 1998 as a stand-up type of arcade game. The idea is you have a controller that you work with your feet, and it can tell what arrow that you have pressed down at a given time, and you're just trying to hit the buttons at the right time. It's generally a genre called a rhythm game, and Guitar Hero is the exact same type of game, except you're twiddling the frets instead of your feet. StepMania is an open source C++, SDL, and OpenGL re-implementation of Dance Dance Revolution. And originally in our discussions, we were like, well, maybe we can add some QML to StepMania. It's a very large project. It's about 150,000 lines of raw code. I got that number with WC. Not the most scientific way to measure code, but it's a lot. So it turns out that QML really fits this type of game so nicely that we actually re-implemented most of the game without using any of this StepMania code. And we got pretty far, and we'll talk about the challenges and some of the things that were easy and some of the things that were hard. So here was just a simple screenshot of the application as it turned out. It's definitely not a full implementation of StepMania or Dance Dance Revolution, but it gets the gist across. In fact, I'll play the game here for a second to get a feel for what's going on. So we can go ahead and run this application. And we'll see, basically the idea is, as the arrows go up, you want to hit the correct arrows at the right line. It yells at you if you're off and rewards you when you're not. You'll notice that the game has some interesting finishing touches. So like you'll notice that the score scrolls evenly, even though we increment in amounts of 100 or 500 or even 1,000. And the life bar is actually also animated with a bit of pulsing and also animates backwards as I start to die. We're playing music, we've got a music video in the background, and we've got the animated arrows scrolling up. And we also can die if you stop hitting buttons. So let's go ahead and take a look at how this was built. And we did this over the course of 2 weeks, and I'll tell you what happened in those 2 weeks. So it turns out that Qt Quick is very good for making a game just like this, mostly because QML is based around an animated sprite field. You can pretty much think of all the QML items as sprites, and you can move them in an animated fashion. This is exactly what this problem requires. It also has the ability to animate almost anything, including the score rolling up. You can tell a variable, when you change, you're just going to have a numeric property animation, so your score can look like a speedometer, odometer rolling over, and not just teleport from 500, 600, 700. Some of these things become trivial just because they're built into the language. So animating those arrows up on the board became super easy. So we used the configuration, the dance files from StepMania. And it's basically some music, a background image, and a video, and a very large text file that's formatted, in the StepMania format. When we're able to derive millisecond offsets for each step, when we need to expect each step to be run. And there's also a beats per minute that we're given. So basically, we start the items at dance line plus whatever pixel offset they have, based on the amount of milliseconds we know that they're going to be fired. And we just simply tell QML, I just want this arrow animated up at negative beats per minute. And the arrows will just evenly slide up the screen. The game, as it's written right now, you'll be able to download the source code of this to see how it was implemented. And we took a simplistic approach to most everything that wasn't the sprite field and the gameplay, including all the arrows that scroll up the screen are created at start time. There could be efficiencies gained by only creating the arrows as they appear on the screen, but it's just more code and more complexity. So as you look at a game such as either StepMania or Side Scroller, something that always comes to mind is it would be really nice to have collision detection. If we could just tell somebody else, well, just tell me when the arrows collide with the dance line. That is not natively available in QML, even though the base of QML, QGraphics View, does have collision detection. So for this particular problem, collision detection wasn't available, and we actually figured out we didn't even really need it. If you do need collision detection, you can expose collision detection from QGraphics View, which we'll talk about later when we talk about the other game. Or you could use something like QML Box2D, which is QML bindings to the Box2D physics engine. So keep that in mind if you do want something that's going to be portable and move forward to Qt 5 that needs collision detection. So we turned out to use two different ways to figure out when to score positive points and negative points. The first is we clear anything above the dance line on a simple timer. You simply get negative points for everything above that remains above the dance line. And every time you step on the pad, we check the arrows to find out if there are any overlapping the dance line. And we can do that pretty easily in JavaScript by just checking the y coordinate of the items. So if we go back and look at the game again, so basically the idea is that if we have the arrows down at the right time, they get sucked into the arrow, you get positive points, and they will simply disappear once they leave the screen, and you will be scored negative points, and your life bar goes down. So the logic to that turned out to be pretty easy and doable without collision detection. When we talk about the next game, QML Bounce, we will actually use collision detection. So something that you get for free that's not a problem, in fact, a massive benefit when using Qt Quick is the Qt Mobility provides Qt Multimedia QML bindings so that you get an audio item and you get a video item. This is how the music video and the MP3 for the game are actually played. It is tuned per platform, so there's differing backends. So on Windows, you'll get one with Direct Show. On Symbian, you get the Symbian Multimedia Framework, and on X, you would get X Video or OpenGL. It is tuned per platform, but be warned, when you try to use it, Qt Mobility is very hard to build on the more obscure platforms like Windows. You need to collect yourself an obscure number of SDKs, and Qt Mobility tries to be too handy, or too helpful, I guess, when building itself. If it's building and it finds that you don't have a particular library for, say, the video item, it will just silently not build the video item. So keep that in mind if you're building Qt Mobility for Windows, for the Mac, or for just Linux embedded. But because of the multimedia capabilities of Qt Quick, the game became even easier because we didn't really have to do any work to display the video or the music. We simply used the QML items. One thing that was strangely hard was reading text files off the disk, or reading any files off the disk, because QML and JavaScript really don't have the concept of like QFile and to open things and to process. Once you have the text in JavaScript, it's actually really easy to manipulate text, and you have access to the regular expression parser from JavaScript. Simply looking at the documentation, it was rather ironic that it was immediately obvious how to fetch a file from like a web service using like XML HTTP request or something similar. However, we discovered that if you ask XML HTTP request to fetch you a local file, it will. So that's basically how we loaded the step files to process when the step should be available. Something like this would be easily solvable by plugging in C++, calling back, doing your processing there. So when it came to graphics performance, the Qt Quick is based around a animated sprite field. And you can, if you have hardware with OpenGL acceleration, you can ask QML Viewer or your declarative view to simply use OpenGL. So performance for basic games isn't really an issue. JavaScript you do have to keep an eye on. It isn't the fastest language in the world, so you need to be careful when manipulating large data structures, such as a large array of arrows. Avoid, of course, repeatedly looking up items. That applies to any language that you're using. And one interesting thing is that local variables in JavaScript are much faster than global variables. So if you're accessing the same structure all the time, sometimes it can be faster to copy it to a local first. Also, don't confuse the QML portions with JavaScript portions of your application. Things in the declarative language, such as the items, are processed at startup, and graphics items and actual C++ animations get generated. Like if we go ahead and look at gameplay, we'll find that things like creating would be a good one. Things like creating things like items and texts happen relatively quickly. Once they're created, they animate fairly fast. However, anything in a signal handler like onCompleted and you call hunks of JavaScript, whether inline or to JavaScript files, you're going to have to keep an eye on performance. One nice thing about the new version of Creator is the QML profiler. By just reading the code, it's sometimes not immediately obvious where your performance problem could be. Is the performance problem from animating 50 or 60 items, or do I actually have some mistake in my code where I'm iterating over way too many items and checking things that I don't need to be checking? Using the QML profiler, you can profile your JavaScript and figure out where your application is actually spending its time. It might not be in the area that you think it's wasting time. So one thing we also had to deal with was the dance pad, which for us turned out not to be a real problem. If you needed something that had a true joystick, this ends up just being a joystick with buttons, you'd have to do some modifications and add something to Qt to understand something along the lines of a joystick event, or map it into something where you can get like the relational axes of the input sticks. Since we had a joystick that only had buttons on it, we simply told X11, we want to map these joystick buttons to key presses, and we'll process those key presses as input to our application. It was really easy, expedient, and most platforms have something like that available if you're on Windows, Linux, or the Macintosh. If we actually needed to process analog sticks, then we would be in trouble. One of the thoughts as we were kicking around the idea initially is that imagine if you had a MeeGo TV device, and this was the type of thing, games that you could download directly to your TV or set-top box, just plug in a game controller and start playing. If you want to do something like that, expect to do a lot of work. So, and another question is, and this is where QML works out really nice, is how can the art staff be involved in making this pretty? So while Tej was off developing the back end of the code and using stand-in art, basically some rectangles so he could verify that the arrows were roughly in the place he thought they were, the art staff went ahead and made us some arrows, some graphics, and actually a whole font. During the development time, while Tej was tuning the game, the art staff actually contributed the art to the project. So we were able to draw in more resources than we normally would if we just had a C++ application. You normally don't want your artist actually touching the compiler or C++ code. They quickly get in over their heads. In fact, the art staff ended up re-implementing most of the art from StepMania. We had planned to reuse it, but it was just easier to get the effects we want if they just made their own sets of arrows. So the question is, how long did this take? So we basically went ahead with one developer and an artist, and only about 2 weeks' worth of work went into it. The idea was we wanted to find out the hard parts and the easy parts to writing a sprite-filled game in Qt Quick. And it turned out to have roughly a week or so in looking into StepMania, how it processed its files, and replicating that in JavaScript. Laying out the game logic, and then the art staff tuning the animations and integrating the final art. Of course, we are not nearly feature complete. We basically have a single-player game. It scores. It's OK. We're still missing multiplayer, per-session skill level, dance step holds. But for 2 weeks, we got a good-looking, fun, playable game, which I think speaks a lot to the productivity of Qt Quick. So how big is it? I mentioned that StepMania was gigantic, and it is. Thousands and thousands of lines of code. In 2 weeks, we ended up with about 700 lines of QML and 400 lines of JavaScript, about 1,100 lines. The difference is so huge, well, one, because it's not a full implementation. But to fill out the rest of the features, would we need twice as much code, 3 times as much code? It's still far less code than I see than, well, StepMania would be at thousands and thousands. And part of this is because we, from the language, get the animation framework for free. We get the multimedia framework essentially for free. And it's a language based around sprite fields, which just makes this type of application a natural fit. So as part of this, as it was originally thought, this presentation would consist of now me, us playing the game for a little while and seeing how we could do. But unfortunately, as I mentioned, my equipment is stuck in customs. I will show you guys again the app in action, and then we'll go ahead and take some questions. So once again, it's very simple. We took a lot of shortcuts in developing it. Mostly we want to find out what the process would be like and what things got hard and what things were easier. But you'll see it's smooth, it's animated, it's fairly polished, mostly because the art staff is good at that type of thing. And we inherit a lot of things directly from the toolkit that we chose. So before we move on to the next game, which is a side scroller, does anybody have questions about what we've done, what we've learned, things that you might like to know? Okay. It's not a terribly complex issue. The next thing I would like to demonstrate is a side-scrolling game that has most of its brains coded in C++ and then exported to QML. This uses the graphics view collision detection. And it's a game that on Nokia developers called QML Bounce. It was actually written by an ICS employee. And Creator does this to me all the time. But this is basically Kolobok. It is a jumping side-scrolling game, and it does parallel act scrolling and collision detection, so we might die or stop. And Nokia developer actually uses the code to this game is also an example for using their in-application purchasing API. This is entirely a demonstration application. It's also really fairly basic. And it takes an entirely different approach. So with the rise of smart telephones, the casual game has really taken off as a market. Casual games are simple games. They don't require much thought, strategy, or plot. They also don't require a lot of time. It's things like Angry Birds that you could play for a few minutes while you're waiting for your code to compile, or you're waiting for your girlfriend to get ready. So you spend 5 minutes here, 5 minutes there. They're easy to pick up, and they're easy to play. And now that everybody has a few seconds of free time here and there and a phone in their pocket, these things have become popular. So this is an example of a side-scrolling game that's easy to play that you might play on your phone or whatnot. It is a side-scroller, which means that your character moves from left to right and the scene scrolls around it. Generally, these games revolve around some sort of collision detection. I've hit a wall. I've hit a bad guy. I've shot at a bad guy. He should now blow up. A bad guy has shot at me. I should have some life deducted. So QML is also pretty good at side scrollers. Once again, most games are sprite field-based things, and QML is a sprite field-based language. The game board is encapsulated in one big QML element that we can translate around to get our side scrolling. The sprites are QML elements. And we're actually going to export graphics view functionality from C++ to get its collision detection. We can also do parallel act scrolling, which, if you haven't noticed, most side scrollers implement some sort of parallel acts, which means that the background scrolls slower than the foreground of the game. What this does is it gives the game an illusion of depth, because the background has a slightly different perspective than the foreground. So the steps involved, and we'll talk about each one of these, is we needed a level loader, which is actually XML files. And the loader is written in C++. And the loader exports information to QML to build the game board, to decide which sprites go where. We needed to create the background and a canvas, and then add sprites, the logic for player movement, how to use collision detection, and how to scroll the screen. Then adding touchscreen import, keyboard import, adding the sound effects, and finally interfacing with the OV store. So the configuration files look something like this. They're simply XML, spaces are open space for our hero to move in, equals are bricks, C's are cactus, and F is fire. Very basic. We're going to process this in, we're going to load it in C++. The QML is going to load items dynamically in JavaScript based on this information. So to be used in QML, you need to, if you want to export C++, you need to inherit from QObject and either implement a signal and slot interface or a property interface. And here we have two properties that are going to give the row count and column count to basically the table that we have that represents the game. The table consists of what's open space, what's bricks, what's fire, and what's cactus. You may notice a QInvocable macro. This is useful generally when you want to export things into QML. If you want to call back functions, they need to be slots. And sometimes it doesn't make sense for some of these functions to be slots. They're not meant to be connected to signals. They're meant to be called directly. So by using the QInvocable keyword, we're able to tell the meta object system that this function shouldn't be listed as a slot, but it should be callable. And for us, it's important to be callable from QML. So to export our class from C++ into the QML environment, we simply make an instance of it. Here we make it in main, and then we export it to the root context of our QML, and we give it a variable name and a pointer to the Q object we are exporting. Now, inside the QML, there's a magic variable called level, and what that's going to do is allow QML to call back up into C++ to find out information about the game. The actual game board is extremely simple. In fact, it only consists of two QML items. There is the background and then a simple blank item. The blank item is going to be used to parent the objects that we dynamically create. It's also going to make it very easy to scroll the game. So the game items are also simplistic. We only have bricks, cactus, and fire. The bricks and the cactus are very simple. They're just image items. They're wrapped in the component so that we can dynamically allocate them. Also, anything that is located in a separate QML file is implicitly a component. So the question is, in QML, dynamically declaring and allocating QML items, you can do from JavaScript. And here is our build level function, which is calling back to C++ to find out how many items there are in each row and each column of the game board. We then go ahead and use a create object on those components that we had. Once you have a component with an ID, you can ask the component to make as many of those items as you wish. So what we're doing here is we are creating either a rock, a cactus, or fire. So this build level function is called when our game board completes loading. So once we have an item parent, the scene, we can go ahead and dynamically allocate all of the game items. So here is, once again, the configuration file versus how the whole scene looks if you stretched out the side scroller so you could see it all. And from something pretty simplistic, you get something that looks pretty good. And it's pretty easy when it comes to the code. Just need to find out where in the table to create the items. Fire is a little more complicated. If we go back to the game, we're going to see that the fire has some animations on it that actually makes it look like it's moving. And that's actually done by the combination of some pix maps and some animations that are going to change the opacity and the location of the individual images. So the images are going to overlap and look like, well, fire. So basically, once again, simplistic approach, we just took 4 frames of fire, and we created them inside of a single item. And what we're going to do is we're going to vary the opacities and the locations of those 4 layers. And we do this by creating an animation that is infinite. So when you make a animation inline, such as a sequential animation, that can contain a parallel animation that finally executes number animations, basically say, for the life of this item, we're going to run this animation. And it is first going to change, it's going to change the opacity, it's going to change the Y value and the heights. So our images are actually moving around, and they're fading in and out, and it gives us the effect of fire. Now, granted, had we spent longer on this and had more frames, we would have better looking fire. But it's something that you can do without a lot of resources. Sorry, I skipped to the end. Okay. So another interesting problem we have with this game is, since we're using collision detection, and our good friend here, Hero, is a round circle, we need to have a round collision detection area. There are no round items in QML. It is just faster and more expedient to say, well, everything's just generally rectangular. And if generally in QML items, if you wanted a circle, you'd make a rectangle with a radius. Unfortunately, that would also have a rectangular bounding box for collision detection. So we would get about here, and we would be colliding rather than right up against, say, the bricks. So the solution to that is to make a new visual item that is a circle. And it's pretty easy to do. You can inherit from QDeclarative item, which inherits from QGraphics item, and you can implement here the ellipse item, which provides a elliptical shape, no real graphics to speak of because we're not going to draw into it. We want it for the bounding box. But the most important thing is the shape function, where we actually return a circular painter path. This is going to get us more accurate collision detection. So we use the ellipse item to simply represent a circular area of the screen. Inside of that ellipse, we actually place an image item. And the image is a standard rectangular QML item. The fact that it's rectangular doesn't matter because we're not using it to do the collision detection. We're going to use the ellipse. So actually moving our hero around the screen gets done basically on a simple timer where we're triggering movement. We're taking a look at our velocities in each direction and basically incrementing the playing field. We need to make sure that when we increment the playing field that we're not going to hit something. If we're going to hit something, we should do something like if we hit brick, we're going to want to decrement our speed. In the vertical direction, if we're bouncing, we want to decay. If we aren't going to hit something, we need to move to the next frame, which is basically all this code is doing. We're just waiting for up and down to be pressed. Now, the collision detection we need to get from graphics view. It's not available in the QML API, and actually this won't be available in Qt 5 either. But for the time being, we're able to go back to C++ land, and we are going to add functions to the level object that we're already exporting. We add 2 functions, colliding items and intersected. Intersected is going to find out that after we've actually hit an object, did we hit that object on the bottom or on the side? And we're going to use that to determine how much speed we should scrub off or if we should stop. So it turns out that in QML, you can take your items and pass them back up to C++, and they will appear as Q-declarative item pointers. We can then use those pointers to cast back to QGraphics items and do collision detection with the normal APIs. So here, for every movement, we're going to decide where our hero should go, and if our hero should stop, should he lose life because he's hitting a cactus or a fire? Should he keep moving because he's in fire? These types of decisions. So the game logic is implemented in JavaScript. This collision detection, the heavy lifting, is done in C++. So basically, there's just a little bit of code necessary to do keyboard integration. That's very trivial in Qt Quick because every item has an attached keys property that you can handle on pressed, on released. There's even specific ones. If you're only looking for enter, you can get on enter pressed. And all we are doing is looking for keys down that aren't repeated. We only want individual clicks and deciding how we should increment or decrement our current velocities. So I mentioned that concept of parallax scrolling, where we are faking depth by having the background move slower in scrolling than the foreground of the application. It's very trivial in Qt Quick because we can manipulate the transform property of any item. And those transformations are propagated down from parent to child. So if we have a top-level container full of items, we can just move the top-level container, all the items move with it. Likewise, the background is a single image. We can translate that. So basically, we have these transformations, which are translates, and they have IDs. So now we can manipulate them during gameplay via JavaScript. So when we need to scroll the scene, we basically find out which direction we need to scroll it. We translate the screen by delta x, and we translate the background by 1/2 of delta x. This will give us that illusion of depth. And it's common in pretty much all side scrollers. Touchscreen input turned out to be a little harder than we thought it would be. If you want something that combines both multi-touch and mouse clicks, we had to make our own item. Here we made what we called a multi-touch item. It is also a Q-declarative item implemented in C++, and it just handles all types of events, touch events, graphic scene mouse presses, and also generic scene events. And what we were doing is basically just implementing very basic pressed and released. Don't even care about the coordinates. All we want to know is if we've been touched. This is how we are going to implement these arrows to jump and go side to side with our guy, so he will work well on maybe like a phone. So basically, to handle these touch inputs, we simply make a number of multi-touch items, place them on the right area of the screen, and then we simply set up signal and slot connections to say, okay, whenever the right arrow button has been pressed, we just want to call the JavaScript that we already had for the keyboards that is going to increment and decrement velocities. So sound effects, when you're doing games, you have your choice of just using the mobility audio items, or as was done with this example, we called backup to C++, and we implemented our background sounds, sounds for when you hit different objects in C++ using the Q audio outputs. Basically, this is another class that we export called the sound player, and it just has public slots. So when the game logic says that we've hit something, we might call back up to C++ to play a groaning sound. Ouch, my player's been hurt. So basically, we expose this through the level object. Once again, we simply add more invocable methods to play the background, to play the groan, to play a boining sound when we jump. And we simply just call back up to C++ like we did for collision detection. So another part of this example, there's not a lot to it, actually. You can download the source code for this off of Forum Nokia, is now called Nokia Developer. And it's also an example of the code necessary for in-app purchases, which is entirely done through a class in C++ called the IAP client. And the idea is that you use this library to transfer control of your application to the OV store. They will handle the transaction, the purchases, things available, and then you can get notified when the transaction has either been completed or canceled. So the idea here is that you could sell extra levels, you could sell game items, it could be, well, anything. And the actual process is pretty simple. You just need to define with OV what the available things are to purchase, and then your application needs to find out what the user has purchased and enable those features. So basically, for getting the feature set that can be purchased for your own product, you can use this function, very simple, called getProductData. And this is going to asynchronously call back to the OV servers, and you are going to wait for the product data received signal. And then you'll be able to get what you've already registered for what the user can buy. You can then prompt the user in any way you want to entice them to buy said thing. That user interface part is up to you. Once the user has selected what they want to do, you call back to OV saying, try to purchase this product. From here, your app will basically be taken over by OV. They will be seeing OV graphics for the processing the payments, deciding whether they actually want it or not, and a signal, either purchase completed or purchase flow finished, is going to be emitted, and afterwards you can then go ahead and enable the functionality for the user. And there's also the ability to restore the product back to the way it was. It's a fairly simplistic API, but it gets the job done and also takes a lot of the heavy lifting for processing the transaction onto, well, somebody else. That concludes the demos and some of the talk about games and QML and different approaches that were taken and some things that we learned. Unfortunately, I was hoping for this to be much more of an interactive type of session where we could spend a lot of the time simply jumping on the pad and having some fun. But does anybody have any questions on either the last section or anything at all? Yes?
I'm making a side scroller too, and I'm making a side scroller.
Yes.
And I wanted to ask, have you considered storing levels in QML files so you can add scripts to the levels?
That is an interesting idea, because that would be a lot more extensible for level writers to write their own effects or their own obstacles. I hadn't considered that, but it is a good idea.
Okay, thank you.
In the side scroller, so you're making a lot of calls from JavaScript to C++. Yes. I just want to know what the overhead is about that, and can it be a problem in an heavier game?
Yeah, the callback system, it isn't, JavaScript's not terribly fast, but calling back into C++, I haven't noticed any serious performance problems, nor does the profiler flag it as a problem. So I haven't run into it. Although I have run into writing bad JavaScript code that ends up just being slow.
Well, thank you.
Well, that concludes my talk. Like I said, I work for ICS. We have videos on a thing we call ICS Network. We have training on all sorts of little things in Qt, and we do consulting. Thank you for attending and listening to my talk, even though it's a lot less fun than I was hoping it would be. Thank you.